Hi and welcome back. This is video 1 of 1 on Chapter 9. Now, Chapter 9 introduces us to the concepts of current and resistance. That said, current is, by definition, the flow of electrical charge. Now, up to this point, we've dealt with situations that are called electrostatic. So, for example, if you were asked, for example, to find, the electric field at a certain distance away from a charge, or find out the force exerted from one charge on another charge, um, those charges were considered to be stationary. Now, we're going to begin to gradually transition away from that, and the first big step we need to do, or we need to take rather, in order to do that, is to talk about the concept of current. Now, if you were to go out to the ocean and watch water as it flows by, you would call that current. And we call the flow of electrical charge current as well, because in many ways we think of the flow of electrical charge kind of like the flow of water. So, electrical current has a definition. The average current is defined as the change in charge over time through an area. Okay. There is an instantaneous, so this right here would be the average. And just like most other physical quantities, you have an average and you can have an instantaneous as well. And that would be just the differential version of it, like this. Now, that said, if you look at the units, we know that the units of charge is the coulomb. The unit of time in the MKS system is the second. And coulombs per second are called amperes. Abbreviated amps. Typically it's the letter A that we use to denote it. So, for example, 1 amp would be 1 coulomb per second flowing through something. Now, that said, let's just do a quick, simple example. In this case, what is the current passing through a wire that moves? 15 coulombs in 30 seconds. So, here our charge, which I'm going to use lowercase q just out of habit, is 15 coulombs. The amount of time that we're looking at here is 30 seconds. So, the average current passing through would be just the charge over time, which would be 15 coulombs for every 30 seconds, or 0.5 amps. Okay, so very easy to do. It's one of the reasons why there's only one video here. Now, that said, in a circuit, for example, here we have a battery. Batteries deliver electrical potential, voltage. And let's not forget that the long side of a battery is considered to be the positive side, and the short side is the negative side. And here, this symbol right here typically means like a light bulb. It's some sort of component, so we'll call this a light bulb. Now, the conventional direction for the flow of current through an electrical circuit is from the positive side to the negative side. So if I were to draw an arrow just sort of denoting the path of current flow, it would be like this. And we use the letter I in circuit analysis to denote it. Now, so let me just write this here. The conventional direction for flow is from positive to negative. Okay, so it flows around the circuit like this. This is not the actual direction that current flows. So, this is a good example of some of the issues that sciences like physics or astronomy or chemistry have. And The issue is that we knew conceptually about current as being the flow of charge, but we never really knew what was flowing up until, say, the late 1800s, early 1900s. So originally, it was believed to be positive charge carriers, positive things were moving. But through experiments like those done by Millikan, who determined the smallest amount of charge that would be unbound, which was the same charge as that of the electron. And through experiments like Rutherford, who showed the structure of the atom as being a nucleus that was very positive, with eventually a region of negative that we think of sort of classically orbiting the nucleus. Um, in a circuit, in truth, the things that are flowing 99 times out of 100 are negative charges. So if you think about an electric field pointing from regions of high potential to low potential, so let's not forget the lesson of voltage and electric fields as they point from positive towards negative like this. Well, it's that same electric field that's moving the current around the circuit. Okay, so here the electric field would point this way, like that. But in truth, what's moving here um, would be the free electrons that you see that accompany metals. So you have these things that are called charge carriers. Charge carriers are basically anything that can move to allow the flow of current. And in a metal, the charge carriers are the free electrons that you have that sit on the outer shell of an atom, specifically metals, that kind of hop from neighbor to neighbor. So they flow by hopping from neighbor to neighbor. Overall, we like to think of the metal as having a neutral charge. But as we're going to discover, one of the ways that you can think of a conductor is as though it's a sort of like a water hose that's packed full of water. So when you cram a little bit of water in one end, the same amount of water that you crammed in came out of the other end. It wasn't the same water, but it was the same amount. So that's the same thing that's going on here. When you have electrical current flowing around in a circuit, it's kind of like water. It's a densely packed hose, if you want to think of it like that. So if you put in a little bit of charge here, a little bit of charge is going to come out over here. And like I said, what's being moved around the circuit are negative charges. And you see the issue that you have here is that the electrical force we can write as the charge that is experiencing the force times the electric field that is sort of enabling that force to be conveyed. So if you were to pick this direction for your current flow, it would be positive charges that were moving. But in reality, it's negative. So in truth, this is really the direction that current would flow. It would flow this way because it would be flowing against the direction of the electric field, since your charge would be negative. It's anti-parallel. So the conventional direction of current flow, though, is sort of a holdover from when we thought it was positive things that were moving. So, and so much of electrical analysis has been built around that we stick with it flowing from positive and negative, and we sort of acknowledge intellectually that in truth, it flows from negative to positive. Now, there are other situations in which you may have positive charge carriers. For example, in a fluorescent lamp, um, you have a gas that's being, we say, ionized, and the nuclei we know are positive. And when you ionize an atom, what you do is you strip off an electron. So you you make that atom have an overly positive charge, if you want to think of it like that. All you've really done is to remove a negative. So those can move and can behave as charge carriers, but even then, primarily was carrying the charge and facilitating the flow of electrical current is the electron, because electrons have so little mass in comparison to anything else. Okay. So that said, what I would like to do now is to take a look at sort of how we view current flow from the subatomic standpoint, or at least from the microscopic standpoint. So I want you to think of a wire as though it's a garden hose. So here is sort of a cross section of your wire here, okay? And it holds its shape because, you know, you have all of these atoms and molecules that are locked into place because it's a solid. All right? So here we'll say are the nuclei of the atoms of metal that make up our wire, copper or something like that. Now, you know, this wire has a length. It has what you would consider to be a cross-sectional area, which means that if you were to sort of cut it in half, you could look at the edge of it, and that would be its area right there. Okay. Now, so these atoms have you know, free electrons that sit on the outer shell, and what happens is when you cram in charge over time, so you know 2 coulombs in a second or something like that, then what happens is every little charge that you put on here pushes neighbors like this way. Now, it's not a straight line. The interaction is very much random. It's a random walk path as it goes through. But the bulk direction is this way. So if you were to put in, for example, 2 coulombs per second, or 2 amps, you would have the same amount come out over here. Now, to be very clear, it's not the same charge. It's the same amount of charge. Okay? You're not looking at the same electrons that were crammed in over here. Now, that said, let's think about, we'll say, a cross-section of this. Maybe this little bit right here. It has a length, which I'm going to call dx. And, you know, we can ask the question, you know, how much charge is passing through here. So that would be dq, the differential charge. Well, okay. So remember, it's the charge carriers that are carrying this. And, you know, different metals have different numbers of charge carriers. One metal, for example, like copper, has 1 charge carrier per atom. You might have others that have 2. Okay. So what I'm going to do is I'm going to call a lowercase n the number of charge carriers per volume. Okay. And I'm going to call Q the charge of the carrier. You know, so, you know, in a metal, the charge that you would see being carried along would be that of, you know, the electron. In a plasma, which is a superheated gas, one that's been ionized, perhaps singly, doubly, even, you know, entirely. You know, the charge carriers would be a combination of electrons, but also a combination potentially of nuclei. And nuclei, we know, could have anywhere between, you know, 1 proton sitting in the nucleus to, you know, wherever we end up finding the periodic table ends at. Okay, so so it's not just limited to that of the charge of the electron. Okay. So, so here, for example, if I wanted to look at the amount of charge that was sitting, we'll say in this little volume right here, um, you would have Q on each carrier. N would be the number of carriers per volume you have. So right here, this is the number of charges per volume. So what volume are we talking about? We're talking about this. It's like a cylinder, right? And the volume of a cylinder like this would be A times dx. This would be the volume, which I'll call dV. Okay. So it would be A times dx. All right. So if I wanted to relate this to current, and current, remember, is defined, at least the instantaneous version, as dq dt. Okay. Then it would be q in a dx dt. Now, the number of charge carriers per volume for a particular metal is a constant. That doesn't change. And the charge itself doesn't change. The area we're going to assume is nice and regular. Okay? So we're going to assume it's constant. So really the only thing that is changing over here is x, hence the dx. And if you were to go back and look at, University of Physics 1, dx dt is velocity. Okay. So we're going to call this v sub d for drift velocity. And the reason is because of what I told you earlier. These things, as they interact with these nuclei, they follow sort of a random walk path like this. So they're drifting through. Okay. So now we have a relationship between the macroscopic thing, which is something that we can measure directly, and the microscopic thing, which describes the behavior of the individual charge carriers as they flow through. Now, that said, here I have a fluorescent light that draws 1.5 amps of current when turned on. Now, it's connected to a light switch, and there is 3 meters of wire between the switch and between the switch and the light. Now, you'll notice here it says 12 gauge wire. Okay. Gauges are one of the methods that we measure the diameter of wires. The smaller the gauge, the bigger the diameter. And 12 gauge wire is typically what you would wire a house in. It carries anywhere from 15 to 20 amperes of current in a normal electrical circuit, or a leg of, we say a leg of your house wiring. If you were to go out right now and say take a look at your fuse box or your breaker box, you would see that many of the breakers, in fact the vast majority of the breakers, are rated at 15 to 20 amps. And that's because they're sitting connected there to 12 gauge wire. Now, we're also told that the wire is made out of copper. Now, this is going to help us because what this does is to tell us not only the number of charge carriers that you have per volume, but it also tells you that there's one per atom, because copper has one charge carrier per atom. Now, what we'd like to do is to find out how long it's going to take for this electron to get from the switch to your fluorescent light. Okay. So what we're given here is that we have 1.5 amps of current. We have a distance, which I'm going to call, just for the sake of brevity, delta x. It's 3.0 meters. Now, 12 gauge wire, if you look that up, it has a diameter of 2.053 millimeters, which would be the same thing as 0.002053 meters. Now, we're told that again that this is copper, and the process that we want to make to find the number of charge carriers per volume here is to look at the molar mass. Now the molar mass of copper is 63.54 grams per mole. Okay, and knowing this, what we can do is we can figure out how many atoms there are per unit volume. Okay, by looking up the density of copper and using this, we're gonna get to that here in a moment. Okay, now given that it's copper, like I said, it's one charge carrier. And the magnitude of that charge is going to be, 1.6 times 10 to the, minus 19th coulombs, because it's that of an electron. So what we're trying to find here is the amount of time it's going to take for this thing to get from the switch to the fluorescent light. So if you take a look, we have the equation that we just derived, which says that the current is going to equal to the charge on each charge carrier times the number of charge carriers that you have, times the area times the drift velocity. So the goal here is to find the drift velocity, and then from the drift velocity and knowing how far we have to go, this drift velocity is an average velocity, so we can just use distance over time to find out how long it's going to take. Okay. So V sub D here is going to be I over Q in A. Now, so how do we find these things? Well, A is the cross-sectional area of your wire, and we have the diameter. We know the area of a circle, because it's circular from cross-sectional standpoint, is pi times r squared. Or if you were to put in the fact that the radius is 1/2 the diameter, it would be 1/4 pi times the diameter squared. So this is our area. Now, the number of charge carriers is a little more complicated. So we have right here our molar mass. It's 63.54 grams per mole. If I were to rewrite this in terms of kilograms, that would be 0.06354 kilograms per mole. So the number of charge carriers we have here, we're going to get by taking a look at this. Okay. Now, so just to remind you, we know that for every mole of substance that we have, there's 6.022 times 10 to the 23rd atoms. Okay, so here we know that 1 mole of copper has a mass of 0.06354 kilograms. That's looking at this and flipping it. Okay, so what we've done is we've multiplied it by Avogadro's number and then divided by the molecular mass. Now, if you look up the density of copper, which for the time being I'm going to call rho, we're going to discover that we're going to need to be a little bit different with respect to the notation. I'll call this mass density. Okay, so rho sub m. The density of copper is 8,960 kilograms per cubic meter. So if I multiply this by the density of copper, 8,960 kilograms per cubic meter, what this gives me is the number of atoms per cubic meter that I have. And remember, N is a number density. It is the number of charge carriers per unit volume, per cubic meter in the MKS system. So what this does is to give me N. Okay, So in reference, or for future reference, the number of charge carriers that you have is going to be this number that we get times whether it has one charge carrier per unit volume, two charge carriers per unit volume, etc., and so on per atom. All right. So if you were to do this calculation here, let me get my calculator. That's going to be 6.022 times 10 to the 23rd. This is 8960. And then divide that by 0.0654. So I'm getting something like 8.25 times 10 to the 28th. Now, atoms is sort of a bogus unit. We're looking at the number of things per unit volume. So the units here at the end of the day, when you cancel out stuff like this, is just 1 over cubic meters. Okay. So here, I have N. I have a form for A. So let me go ahead and plug that form for A in. That's 1/4 pi d squared. Or if I flip that to the top, 4 times I divided by Q n pi d squared. This is what we're going to work with. So 4 times I is 1.5 amps. Our Q is 1.6 times 10 to the minus 19th coulombs in magnitude. Our charge density we just got, we have a pi there, and then we have a d squared, and d is 0.002053. So what's our drift velocity? Let's see, 4 times 1.5 divided by 1.6 times 10 to the minus 19th times pi times 8.25 times 10 to the 28th times 0.002053 squared. And I get something like 3.43 times 10 to the minus 5th meters per second. That's incredibly slow. Okay? So let's figure out how long it's going to take for this to go 3 meters. So velocity, if it's constant velocity, which is what we're assuming here, is just distance over time. So our time is going to be the distance over my drift velocity, okay, which is going to be 3.0 meters divided by 3.43 times 10 to the minus 5th meters per second. So if I were to take 3 and divide it by that, I get 87.392 seconds. So I'm going to take this and let's divide this by 3600. If I divide it by 3600, that makes it about 24.27 hours. So, it's a good thing that we think of, electrical current this way. Because if we had to rely upon that original electron being the thing that traveled through, then whenever you wanted to turn the light on in your house, you would have to flick a switch and then go about your day as normal. Take a nap, have dinner, go to bed, etc., and so on. And then when you woke up the next day, roughly around the same time that you flicked the switch, the light would come on. Pretty crazy, huh? Now, so, that said, what I'd like to talk about now is sort of an extension from current called current density. Now, current, again, if you think of this, is something that's flowing through an area. If you think of the wire as having area, okay? And we've seen things that have flown through area before. Specifically, I'd like to remind you of electric flux. Okay, electric flux is, how much of an electric field that flows through, some sort of differential area that you've drawn. Well, current is something that's flowing through an area, a cross-sectional area of a wire. So you can think of current sort of as though, and this is not entirely true, but it's sort of like charge flux when it's moving. Now, what we typically do is we make a vector, we call it J. This is called the current density. And we look at how that passes through an area. And when we do that, you get your current that's passing through it. So J itself is called current density. If you look at its units, J's units are amps per square meter. All right. And like I said, this is a lot like flux. So, if you were to say, just do a simple example here, what's the current density of 20 amps of current passing at 25 degrees with respect to the surface of area 0.5 centimeters squared? So you can think of this as though it's electrical current that's flowing through some area. So you have your current density that's flowing through. Now here, I is 20.0 amps. We're going to assume this is constant. Our area is not changing, and as a consequence, our current density is constant. Now we have an angle here. It's 25 degrees. We have an area that is 0.5 square centimeters. We're going to need to convert this to square meters, noting the fact that, for every 1 meter, you have 100 centimeters. So this would be the same thing as, 5 times 10 to the, let's see, minus fifth meters squared. So this is what we're given. And what I'd like to try to find here is J. Okay. Now, so I is equal to the integral of J dot dA, A being our area. So the way I envision this is that if you were to look on edge like this, this would be your J passing through like that. And this right here would be your surface normal. It would be along this direction like this, along this axis right here. So the angle that we have here is this one right here. This is theta. And this is a dot product. J is constant, dA is just an area. So in that situation, this is just J dot A. Okay. A being the area times the normal. Now, again, when you do this dot product, you get J times A times cosine of theta, and J and A are both magnitudes. So my current density here is going to be I divided by A times cosine of theta. And that would be 20.0 amps divided by 5 times 10 to the minus fifth square meters times cosine of 25 degrees. So let's see here. 20 divided by 5 times 10 to the minus fifth times cosine of 25. And I get it's like 4.4 times 10 to the 10 to the fifth amps per square meter. Now this looks like a big number, but look, in reality this is flowing through a very small area. So there's really not a whole lot of amperes. It's only 20 amps. So like I said, just a quick example. The reason why we like to talk about current density is that as you do more advanced subjects under the umbrella of electricity and magnetism, many times the current density is the thing to talk about and not current itself. Alright, so that said, what I'd like to talk about now is something called resistance. So if you go back and you look at the picture that we drew here, and in fact I'm just going to borrow this. So here, we're putting in charge over time here, and it comes out over here. And as the charge passes through our wire, then what happens is you have this random walk as that electron or that charge carrier interacts with the atoms and molecules that are on the inside. So there's going to be some opposition to getting it through. As a consequence of this interaction, it's kind of holding up the people that are waiting to go in line, right? So if you were to look at the relationship between the charge density that flows through here and the electric field that you need in order to drive it through, they're going to be related to each other. They're proportional to each other. Okay? So, which should make sense because what's moving the electrical charge through here is right here, the battery. Okay? The battery creates a potential difference, which creates in turn an electric field. So it's this field that's moving the charge. Now, I want to be very clear about what's going on here. If you remember our conversation about electrostatics, one of the things we noticed was that conductors have no electric field that sits on the inside. But that was in a static situation. So here it's entirely possible to have this field passing through. The field passing on the outside. Alright? Like this, pushing stuff along. Now, that said, our current density here, okay, is proportional to the field that it takes to push it through. And that proportionality is a manifestation of how easy or how hard it is to get the stuff to go through. Typically what we do is to write it the following way. It's something called sigma times E. Now sigma itself is a new thing. I know in the past we called sigma surface charge density. But sigma is also used to refer to something called conductivity. Now, conductivity has units of 1 over something called the ohm times meters. Now, ohms are units of resistance, and we use the Greek letter omega to denote them. Okay? So our conductivity has units of 1 over ohm meters. There's another version of this constant that sits out in front, and that's called resistivity. Now, resistivity, we use rho for. It is 1 over conductivity. Okay? And its units are ohms per meter. Or ohm meters, rather. Now, it's this stuff right here, this resistivity, that we're really interested in. And that's because resistance is opposition. And as I mentioned, the act of these things sort of taking this meandering path through causes resistance. It causes opposition to getting more guys in quickly. So, if you were to look at the relationship between the field that it takes to push this stuff through and the actual current that's going through, or the current density that's going through, what you would see if you plug this in and solve for it is that the measure of how hard it is to get stuff to go through is just the electric field divided by the current density. Okay? So one of the ways that you can determine resistance overall is by looking at how much electric field it takes to move stuff and how much current is moved through the area over that time. Now, that said, this is useful, like I said, from a more umbrella standpoint because it's related to the current density. What is directly useful to us is the fact that it takes work to move this through. Now, we know the electrical analog of potential is voltage. And it may not be all that surprising to discover that if there's a relationship between current density and the electric field, since work and potential energy are related to the forces that are doing it, then electric potential, which I'm going to call V, would also be related to how much current that you can move through. The way to think about this is that the more current you want to move through, the more work you have to do it. Now, the constant of proportionality that we have here for this is something called R, and this is resistance. It is measured in ohms. Okay. Now, so that said, let me give you sort of a visual idea of the way to think about this. So we know we can think of a wire as though it's just a hose carrying water. So there's our hose. But if I want to restrict the flow of water, what do? Well, I crimp it. I crimp my hose shut like that. And what that does is to make it very hard for my water to flow. It gives it resistance, opposition. So here, this symbol right here, this crimp, is the same symbol that we use for resistors. And all resistors do is to offer opposition to the flow of current. Now, as a consequence, they eat up energy. So they take some of the energy that you're trying to move that current through with, and they turn it into heat. So resistors transform electrical energy into heat energy. Okay, very important component in an electrical circuit. Now, because of that, that means that they're susceptible to having their sizes change because they're getting heated up as stuff pours through them. And so you can apply what we've learned in thermodynamics, for example, to talk about how resistance can change as your resistor does its job. Now, resistors are typically made out of graphite, other materials. They're conductors that have very, 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 very high opposition to getting stuff moving through them. Now, there is a relationship between R, the resistance, and rho, the resistivity. And the way to think about it is the following. So let's pretend that this is a resistor right here. So this thing right here, what we're going to do is we're going to dump current into it. Current's going to flow out of it, the same in, same out. But how difficult it is to do it, well, that depends upon the resistance. And this thing is going to eat up some of the energy that we're trying to move this current through and transform it into heat energy, right? So it has a length. This resistor has a length. Now, will you agree with me that the more crimps, the longer the number of crimps. So if you crimp your hose more and more and more and more, what you're doing is you're making the area that's being crimped, the area that's offering resistance, longer, right? So the longer your resistor, the more opposition that you're going to have. And what you discover is that if you look at the relationship between R and how long that thing is, it's a direct proportionality. Okay. Now, that said, you also have the caveat that the bigger the diameter of this thing, so the bigger the radius, right? The bigger the area. That means that there's more room for these things to random walk through, which means that there's less opposition. And if you look at the relationship between area and resistance, it would be 1 over the area. It's a direct relationship for what we call linear materials, which is what we like most resistors to be. So your resistance is proportional to the length of your resistor and 1 over the area of it. And if you were to sort of follow this through, what you would see is that the physical definition of resistivity is that constant that sits in front to handle this. Okay. Now, so we have a length here, and we know that when you heat stuff up, lengths can change. Primarily, it's the length that changes, and not the area here. And so you have the relationship between final lengths, initial lengths, and coefficients of thermal expansion. So another way you can think about resistance is that if you wanted to see how it was affected by temperature, it's going to be your initial resistance times that right there. And all you're doing is plugging this in for that. Okay, so now we have a relationship that tells us about how resistance changes with respect to changes in temperature. Now, so that said, this right here has a formal name, just like this right here has a formal name. They're actually both named the same thing. These are called Ohm's law. Now, this says that there is a linear relationship between how much current you're trying to pass through something and how much work you have to do it. Materials that obey Ohm's law are linear materials. And assuming you're operating within a good temperature range, many materials are linear in nature. Okay, so Ohm's law is a very, very good approximation to resistance in an electrical circuit. So as an example, what I'd like to do is to look at this problem right here. We have current passing through a resistor. Our source voltage is 12 volts. our resistor is 100 ohms, and as you can see, I have it crimped right here. What I'd like to know is how much current's passing through, and I'd also like to know if I were to change the temperature of this, okay, by 50 degrees Celsius, I'm going to raise it. I want to know what the new resistance is going to be, and also what the new current that flows through is going to be. Now, most resistors are graphite, okay, they're carbon. So you can very easily look up the coefficient of thermal expansion for carbon. And let's see here. If I write down what I've been given, source voltage is 12 volts. The resistance is 100 ohms. Carbon, our resistor, has a length of 2.0 centimeters, which is 0.020 meters. That may or may not be useful to us. We have a change in temperature that is 50 degrees Celsius. And if you look up the coefficient of thermal expansion for graphite, it's about 7 times 10 to the minus 6. 1 over Celsius degrees. What we're trying to find is I, and then I'm going to call it I new and resistance new. Okay? So the first thing we're going to do is to find I. And to do that, I'm going to use Ohm's law. V is equal to I times R. Because I know my resistance and I know my voltage. So I here is just V over R, which would be 12 volts divided by 100.0 ohms. Now, so what's 12 divided by 100? Well, that's easy. That's 0.12 amps. All right. So we found I. Now let's look at how our resistance changes. So our new resistance is going to equal to our old resistance times 1 plus alpha times delta T. Our old resistance was 100.0 ohms. 1 plus alpha, which is 7 times 10 to the minus 6, 1 over Celsius degrees, times delta T, which is 50 degrees Celsius. So what do I have here? So 7 times 10 to the minus 6. This is 100.035. Now, it's not that big of a change of resistance, but if you were to have, say, a circuit that had a whole bunch of resistors in it, and they all experienced this change in temperature, there is a good chance that you would see a substantial change in resistance, which could cause problems with heating and also would cause your circuit not to behave as expected, because circuits are designed with specific resistances and things like that in mind. So this is my new resistance. What's my new current? Well, following this right here is going to be V over R sub n, which would be 12 volts divided by 100.035 ohms. So 12 divided by that, which is going to be, 12 divided by that, not 10. .11996-ish amps. Now obviously the sig figs here aren't right, but as you can see though, it definitely changes things. Okay, there is a small change as a consequence of heating. Now that's not just going to affect the resistor itself. Anything, with the exception of a certain class of materials called superconductors, that you try to pass current through is going to have resistance, and that includes copper wire. Okay. For example, if I were to look up a table of resistivities here, as you can see, you have resistivity, you have your thermal conductivity. These are all basically the conductivities and resistivities that you see. But take a look here. Houses in general are wired with copper, and copper has got this resistance right here. I mean, it's microohms per centimeter, okay, which is not a whole lot, but it adds up over distance. Aluminum has got this right here. Now, if you've ever had the pleasure of living in a very old house, there's a chance that the wiring inside your house isn't copper, which is what it is these days, and instead it may have been aluminum. And if you live in a house like that, you're kind of stuck with a nightmare there, because aluminum wiring over time can cause electrical fires, and that's because aluminum isn't nearly as malleable or ductile as copper is. And as your house expands and contracts due to normal heating and cooling over the course of time, then what that does is to cause your aluminum rather to stress and fracture and cause shorts. And when you have shorts, that can cause electrical fires. Okay, and also the stuff that the aluminum wiring was wrapped in is just horrible. Okay, so as you can see here, nothing on this table has a zero resistivity. But like I said, there are classes of materials that are called superconductors, which we're not going to really spend any time talking about. And superconductors operate at very low temperatures, and as a consequence, the low temperature has an effect on the material and causes what in some cases are called Cooper pairing. And what that does is to allow your electrons to sort of pass through without any real issue. And as a consequence, these materials have zero resistance. The caveat is that it requires low temperatures in order for that to happen. And by low temperatures, I don't mean that you take it to the North Pole and you're all good. What I mean is that you're talking about temperatures that are on the order of liquid nitrogen or something like that. So they're cool. They are ideal because you don't have energy loss. Like for example, we pipe electricity from a power plant to our house through wires, and those wires are made out of copper. So if we could eliminate the electrical loss due to the innate resistance of that copper and use superconductors everywhere, then you wouldn't have that loss, which means everything would be much, 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 much more efficient. You can also do some pretty cool stuff otherwise with superconductors. We'll actually be revisiting these things when we talk about the magnetic field. Now that said, the last subject that I want to talk about today is power. And that's because in electrical circuits, you actually see power used very frequently. It's probably used there more frequently than any other area of physics. Now, remember, power, just as defined as energy over time, in an electrical circuit, the energy that you are usually operating with is done through voltage, right? And if you remember the definition of voltage, I mean that's just your potential energy over charge. So I could think of power as Q times delta V. There's my energy. All I did was to solve for delta U, and that's over time. Now, in the circuits that we're looking at, where our current is more or less passing through at a constant rate, and and our batteries aren't changing. The potential difference between the terminals of the battery aren't changing. This right here is constant, and really what you have here is voltage times dq/dt, if you want to think of it like that. And this right here is just current. So there's a relationship between power, voltage, and current that's very easy. Now we can also use Ohm's law, which says that V is equal to I times R, and rearrange this. And there's three ways that you see the power equation usually written, and they're all equally useful. If you were to plug this in for V, one way would be I squared times R, and if you were to take and solve for I and plug it in, another would be V squared over R. So there are your three different ways that you can write power. Now, just as an example, what I'd like to do, just to show you how this works, is to take a look at this AC adapter for a laptop. Now, if you look very closely here, and what I'm going to do is to sort of see if I can cut part of this here. I may or may not be able to, because this is a full picture. Okay, so I guess I can't, but what I'm going to try doing here instead is to it's not going to let me do it, I don't think. There we go. So what I want to do is to focus very carefully on this input stuff here and this output stuff here, because as you can see, our input voltage has a range, but it also has a current. You have a voltage and a current. Our output has a voltage and also current as well. Now the output is what's delivered to the laptop in order to charge it. So here, for example, if I were to look at the power that this thing is consuming, this is the power that it's using, it's just I times V. And in the United States, your wall outlet delivers 120 volts of electrical voltage. My I would be 1.5 amps. So from a power standpoint, this thing is using, this is 120 times 1.5, so it's 180 watts. Okay? Now, on the other hand, if you look at what's being outputted, so this is input, this is in from the wall, and this is out to your laptop. I'll call this PI and this PO. Again, I times V, except now my I here is 3.33 amps and my V is 19.5. Now if I do the math on this, 3.33, it's 64.935. So I'm taking 180 watts and I'm putting 64 or 65 watts approximately into the laptop. If you were to look at how efficient this is, the efficiency would be the power out divided by the power in. So if I were to divide this by 180, it's about 36%. Well, where's the loss? Where's the other 74% of the energy going? Heat. So it's the resistance that sits on the inside of this thing, in part, that's eating this up. And if you are charging your laptop, you put your hand on this and hold it, what you would discover is that these things get very warm when they're charging. Anything that gets warm when it's charging a device is wasting energy in this way. So as you can see here, 180 watts in, 64, 65-ish watts out, and it's only 36% efficient. So there's a lot of energy that's being lost here. Now, in the next chapter, we're going to talk more about uh, electrical circuits, specifically DC circuits, direct current circuits. And what we're going to do is we're going to look at circuits that are combinations of resistors and capacitors, and see how those things interplay inside an electrical circuit. And I'll see you then.